So with that, we'll move on from C4 to C5, and we'll look at pentane. So I had a few students come to office hours in relation to a question on the quiz. And so I think it's important that we fill out that total number of carbons first, because that's important, especially with this problem here. So I've numbered the chain. It's 5 carbons. 5 carbons is pentane. So methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane. So those are the ones you should be familiar with. Methane to butane, it is what it is, but after that, like pentane, we know is pent is 5. So after 5, the prefix follows sort of the normal number. Don't want to do that. So this is, the first column is total. How many total CH3 groups are there? So there's 2. How many total CH2 groups? So 3. That means there's 0 and 0. So that gets us 5. The CH3 groups are at 1 and 5. The CH2s are 2, 3, and 4. The methyl groups, are they the same? So yes, the 2 becomes 1. Now this is the issue right here that the students approached me about. You have 3 CH2 groups. Are they all the same? So no, they are not. And to use the laser here, when you go from 1 to 2, carbon 2 sees a methyl group on the left and then a methylene group on the right. Sort of the same thing when you go from 5 to 4, methyl, methylene. Now the difference is carbon 3. When you look left and right there, that sees a CH2 group on each side. That means that even though they're all CH2, 2 and 4 are the same, and 3 is different. So this number is going to reduce from 3 to 2. And so our total unique carbons here is 3. And this is, anyone play softball? This is a home run hit here, so the answer for this one's going to be B. Let's go through the H sets and determine why that is. We've sort of already done an analysis of the attached hydrogens. We see that the CH3s are equivalent. There's 2 different types of CH2s. So that's indicating to us that there's 3 unique sets of H. So 1 and 5, those are CH3 groups. 2 and 4 are CH2, and then 3 is CH2. So those are the 3 sets. The total number of hydrogens would be 6, 4, and 2. So again, the format of this and as I said, the questions on the exams, I try to make them as self-contained as possible. So if you see this type of question, it will say of the format C13, 1H, and then ratio. Question? So the question was, are these two numbers always the same? For a lot of the initial cases, it will be that way. But when it is not that way is here, right here. See the carbon with no attached hydrogens? That's when those numbers are going to be different. So C5H12, the 5-carbon hydrocarbon is called pentane. There's no other way you can combine those. So pentane means that structure. But the question is asking you, there's another constitutional isomer that's a derivative of butane. So to make that, we're going to reduce the carbon count to 4. The parent is going to be a butane chain. So we have one carbon to stick back in there. And the logic of these is you never add it back to the terminal carbons because you're just going to go up from the row you just completed. So we have one carbon. We'll do the most logical thing. We'll add it to carbon 2. And so butane will now become 2-methyl butane. One other way of classifying these, the C5 is called linear. The longest chain with C4, this is called branched. Because now you're hitting a point at a carbon where you can take more than one path. So without going through that whole table again, just visually looking at that, how many unique carbons do you think there are? I think I heard some people say 4. So there's a 4. The 2 methyl groups bonded to, the 2 methyl groups bonded to carbon 2, those are equivalent. You go out from here to that methyl group, here to that methyl group, that's the same path. So that's 1. Carbon 2 is unique because it's a CH group. There's no other CH groups. Carbon 3 is unique. It's a CH2 group. There's no other CH2 groups. Carbon 4 is a methyl, CH3. But it is not the same as these two because of the path. So that gets you your 4. Yep. So the question was, when you're building this up, you're starting from butane and you have 1 carbon. So if I say 1, 2, 3, 4, if I put that carbon at 1 or 4, I'm just making pentane, which is what we already made. You might ask the question, well, let's put it on carbon 3. You can do that, but that compound is not called 3-methylbutane because it's the same as that. So this structure and that structure are the same thing. On the screen, the only difference between them is if you imagine rotating it, you get the same thing. The numbering system we'll talk more about when we get to the nomenclature rules. Yep. Yeah, you're doing it in succession. So there's another isomer of pentane. That's a propane derivative. So we're going to go from 5 to 3. That means we have 2 carbons to account for.
And that's where the different prefixes come in and where you go.
Yes. So because there's no carbons without hydrogens, the hydrogen sets is still going to be 4. So we have 3 plus 3, that's the 6. Those 3, that's that. These 2, that's the methylene, and that 1, that's the methine. The ratio numbers, I just write them in decreasing order. There's no deeper logic to that at all. So 5 to 4, now to 3. So linear, branched. So if n is 5, anything less than n will always be branched. We said this was pentane. This was 2-methylbutane. The last one is a propane derivative, but now you have 2 carbons to put in there. And remember I said you can't stick them at the end. So where do both have to go? On carbon 2. So the longest chain is 3, so it's a propane derivative. So there's the longest chain. Again, I'm not going to get too much into the nuance of the nomenclature because we'll go through those rules later on. You have 2 methyl groups. You have to specify both. They're both on carbon 2. So it's 2, 2 hyphen di. Because of there's 2, we're going to use this numerical prefix di. They're both methyl. 2,2-dimethyl propane. So the answer for this one is A. Both of those carbons go on position 2. So 2,2-dimethyl propane. How many unique carbons does that have? So 2. How many unique sets of hydrogen? Just 1. Because that number's 1, the total has to be 12. Because that's the total number of hydrogens in the molecule. So this is a way of differentiating them, essentially using carbon NMR. So the uniqueness, we said this was 3, that was 4, and that's 2. That uniqueness number corresponds to the number of signals that you'll see in the data. So hexane is linear. How many unique carbons does hexane have? Heard of 3 off the bat. Again, however you want to think about this to get to the right answer, if you want to account for them. So 1 and 6, 2 and 5, 3 and 4. So those are the carbon atom numbers and then what type they are. So pay attention to the wording here in bold. This says total. So how many total CH3 groups are there? So 2, that eliminates B and C. Total CH2 groups. So 4, that eliminates D. So A will be the correct answer for this. So we said in the prior problem, 1 and 6 were CH3, 2, 3, 4, and 5 were CH2. So what you're seeing here is it's a simulated carbon NMR spectrum. So the structure was put in, the computer did some calculations, and it spit out this spectrum. How many, again, the flat line is the baseline, the x-axis is the chemical shift. How many signals do you count? So you count 3. And again, we already determined that hexane has 3 unique type of carbon. And so that's what they will look like. We'll talk later on about where they occur. So their point on the x-axis is called the chemical shift. So that's a discussion for Module 2. So now what I want you to think about, if you're given the choice, say this was A, B, C. This is how the exam question would be phrased in a sense. Given that piece of data, what structure does that spectrum correspond to? So you would go over, you would count these 1, 2, 3. You've done your uniqueness test. So you have to pick A as the answer. If there were 4 signals, it would be, getting this mixed up with the prior one, pentane, sorry. That would be the way you differentiate these. Count the number of signals. Does it match the unique type of carbon? So what did we say? We said there was three type of carbon. Again, another softball question for you. There's the three. There's no carbons without hydrogens, so the sets of H are the same. And this gets you 6, 4, and 4. And again, that's the total number of H. So when you add that, it does equal 14. So I got a little bit ahead of myself on the prior slide here. These are the branched constitutional isomers of hexane, or of C6H14. And again, branched means that as you're moving along the path, you can take another path. So it says which constitutional isomer has the greatest number of unique carbons? So I heard an A. The answer is A, but let's write the numbers down. How many does A have? So it has 5. What about B? 4. C? I heard a 3. I think it's 4. So these CH3, 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 those are the same because they're bonded to carbon 2. So 1, 2, 3, 4. What about D? Just 2. So D is interesting because it has sort of a mirror plane here. So that bisects the sigma bond sort of at a 90-degree angle. Then the other mirror plane runs along the sigma bond. So that has 2 elements of symmetry. So all of these CH3 groups are the same. And then the CH groups, obviously different, but they're the same. Yep. So that's one set. CH is different, so that's another. CH2, a different CH2, and then a different CH3. These CH2s are different because the green one is bonded to a CH and a CH2. This has CH2 and CH3. So we said 5, 4, 4, and 2. So which structure does that spectrum belong to? So this is going to be D because you have 1, 2 signals. So which branched isomer has the hydrogen set ratio of 6, 4, 3, 1? So this is 4 numbers, right? So what I just wrote in red are the unique H sets. So this is a good sort of talking point about when the numbers don't equal one another. The answer is B. So highlighted in the color here are the different H sets. So notice for C, we said there were 4 unique carbon, right? But there's only 3 unique type of hydrogen. And again, the difference is that carbon right here, which would be carbon 2 on the chain, that has no hydrogens. So this is a situation where your reporting of the uniqueness, the numbers differ. So now this is a proton NMR spectrum. The first thing I want to point out, the signals again look different, and we'll explain why that is in Module 2. But what I want to do is just circle the number of signals. So that whole thing is a signal, that's a signal, and that's a signal. So there's 3 signals. From the prior slide, we said this had 5 sets of H, this had 4, this had 3, and then this had 2. So the number of signals is equal to the number of sets. These numbers I've put in bolded black, highlighted with yellow, that's the ratio. So you have 3 sets in C of 9 to 3 to 2. That's what those numbers correspond to. When we actually start interpreting spectra later on, we don't use the word ratio, we say integration. Any questions, even though I don't have a slide for it? So everything we've seen so far today, the molecules only have single bonds, sigma bonds. They're either CC or CH. So hydrocarbons are organic compounds that have carbon and hydrogen. But within that umbrella, there's these different functional group types. So saturated is what we just saw. Saturated means the carbons have 4 sigma bonds. Unsaturated has a carbon-carbon pi bond. That's an alkene. Notice the difference, A to E. Or an alkyne. Now that ends in Y. That's a triple bond. We'll also learn about a specific class of hydrocarbons that are aromatic. And they have typically this form, a 6-membered ring with 3 pi bonds. Notice it's still C and H. So hydrocarbons come from petroleum, which are fossil fuels. I'm of the opinion that electric cars should go away and die. And the reason I say that, they're no better for the environment than fossil fuel cars. If you look up how the batteries for those cars are actually made, they do just as much harm to the environment as combustion gases do from fossil fuel cars. Plus, you don't want to be in a car crash with an electric car, the doors lock and the battery starts on fire. Have you ever seen a lithium battery like just from a phone start on fire. It's pretty scary. So these fossil fuels, they come out of the ground as hydrocarbons, and then they're transformed into other things. And as we're learning about structure, that's going to inform us on reactions and how do we predict the products of a reaction? Like, what are the practical aspects? One of the first reactions we'll learn when we get to Module 4 is we can take a hydrocarbon such as methane. It's nonpolar, has those melting and boiling point properties. We can treat it with chlorine gas, initiated by light or heat to provide the energy. And if you look at this H, that H is substituted for a chlorine. So that's called a substitution reaction. Now you have these two new things. Chloromethane, you've taken a non-polar molecule and you've made it polar. There's the Lewis dot analysis. You've changed the physical properties of the molecule, so non-polar to polar. The point of doing the uniqueness of C and H, with just one carbon methane, you can substitute any of those H's for chlorine and you only get chloromethane. But say you went up to propane. You said there was two unique sets of H, so now which set gets substituted? So the possible products are chloropropane or 2-chloropropane. So which one forms the major product, and then how do you determine that? If you look at the uniqueness sets of those, you'll be able to say, okay, they're different. So when I do get some data of what the product is, I can say, this is the major product. So one thing that we'll need to utilize in understanding the differences of the hydrocarbon classes. So again, ANE, ENE, YNE. And notice down here, cycloalkane. Again, that's not the same as an alkane. The word cyclo does make it different. The general molecular formula, again, starting from N equals 1, working our way up. An alkane is CnH2n plus 2. That means every bond in there is a sigma bond. So all the carbons have 4 sigma bonds. There's no pi bonds. So for example, CH3, CH3, that's ethane. Now if we wanted to change the bonding pattern between the carbons, we could put a pi bond. If you're making a second bond between the two carbons, that means each has to give up a hydrogen. So the molecular formula now changes. You take away these two hydrogens, so it's HN or CnH2n. So each carbon has 3 sigma bonds and 1 pi bond. And then this new term, degrees of unsaturation. So hopefully that saturation versus unsaturation makes sense to you. Saturated is 4 sigma bonds. Anything else is unsaturated. So that has 1 degree of unsaturation, which is the pi bond. If we take away 2 more, we get alkynes, so CnH2n minus 2. That gets us a triple bond. So 2 degrees of unsaturation, pi plus pi. Then each carbon has 2 sigma bonds and 2 pi bonds. A cycloalkane has the same general molecular formula as an alkene, but the degree of unsaturation is not a pi bond, it's a ring. So if you take propane, 1, 2, 3, and you tie together 1 and 3 to make a ring, to make the bond between carbons 1 and 3, you have to remove 2 hydrogens. So that's why the molecular formula, or the general molecular formula, is the same as an alkene. So that 1 degree of unsaturation is a ring. Now keep in mind, we're building up. These are just the CH functional groups only. We haven't started sticking in oxygens, nitrogens, or halogens. When you do that, those are different functional groups. And when you start looking at these problems, you can propose a lot more constitutional isomers. Because remember, nitrogen has the neutral pattern of bonding of 3, oxygen 2, halogen 1. That means you have a lot more flexibility in how you start bonding these things together. So what I've just put those lines in there is, 1 through 3, we said there can only be one structure for those. When we get past greater than equal to 4, you can start having multiple constitutional isomers. You differentiate them according to the name. Again, even though they have the same molecular formula, we figured out the uniqueness was a way to differentiate them as well. And then the melting and boiling points, when we get a little bit later on in the module, we'll start talking about how you can make some explanations of why those things change based on things being linear or branched. So again, alkane CnH2n plus 2. Notice here now the next hydrocarbon functional group, alkenes, CnH2n. In the nomenclature, you're taking ethane and you're making ethene. So the ENE indicates you have a pi bond. So same sort of deal, melting point, boiling point, the state at ambient temperature. Maybe what we'll wrap up with, I talked a little bit long on the first explanation of things, so we're sort of behind on the slides, but if you go through the rest of the slides, which we'll start up again on Wednesday, you should be able to see where the logic is going. I just want to say one more thing before we end. See carbon count 4. See these other terms here, cis and trans. Cis means same, trans means opposite. And then you have these other numbers. So that molecule is called butene. But what if you want to place the pi bond somewhere else? What if you don't want it starting at carbon 1? It can start at carbon 2. But then you have two ways of doing that. This is called trans 2-butene. The 2 indicates the start of the pi bond. The trans means the substituents on the carbons are opposite. The other one is cis 2-butene. So location of the start of the double bond. Cis means same. So carbons 1 and 4 are on the same side for cis, 1 and 4 on the opposite side for trans. So we'll pick up on, Friday with alkynes, and then we'll start getting into molecular formulas that have heteroatoms.